Some materials are supposed to fail. They crack, they weaken, they decay with time. Concrete is one of them. Modern concrete is engineered with precision, reinforced with steel, tested by computers, poured by machines, and calculated down to the millimeter. And yet, despite all of that, it has a lifespan. 50 years, maybe 100 if you're lucky. Bridges crumble, seawalls fracture, skyscrapers rot from the inside out. Now here's the uncomfortable part. There are concrete structures standing today that were built over 2,000 years ago. They've survived earthquakes, they've survived wars, they've survived saltwater, volcanic eruptions, and centuries of neglect. And not only are they still standing, they're getting stronger. This is not a myth, it's not legend, and it's not exaggerated history. This is Roman concrete.
Every piece of technology hides a story of vision, rivalry, and forgotten battlefields. From ancient machines to world-changing inventions, every breakthrough has a past worth remembering. This is the technological past, where history and innovation collide, and the stories of yesterday shape the tech of tomorrow. Subscribe to the Technological Past, because here you'll uncover the hidden stories behind technology, history and innovation that shaped our world, and get a glimpse of the upcoming tech gadgets transforming the future.
A material so advanced, so chemically intelligent, that modern engineers are still trying, and often failing, to replicate it. Because somewhere in the rise and fall of the Roman Empire, humanity didn't just lose a recipe, we lost a technology. And the deeper scientists dig into ancient Roman concrete, the more unsettling the realization becomes. The Romans may have solved problems we still haven't. To understand why this matters, you need to forget everything you think you know about ancient construction. No slaves blindly stacking stones, no crude trial and error masonry, no primitive guesswork. Roman engineering was deliberate, calculated, systemic. They weren't just building structures, they were engineering materials at the molecular level, without microscopes, without chemistry textbooks, without modern science as we define it. And the proof of that genius isn't hidden in dusty museums. It's standing in plain sight. Take the Pantheon. Built nearly 2,000 years ago, its massive concrete dome remains the largest unreinforced concrete dome ever constructed. No steel rebar, no modern supports, no internal skeleton, just concrete. The dome spans 43.3 meters, an engineering feat so extreme that no one else matched it for over 1,300 years. And here's the part that makes engineers uneasy. If you tried to build the Pantheon today using standard modern concrete, it would likely crack. It might collapse. It would almost certainly require reinforcement the Romans never used. But the Pantheon is still standing, perfectly balanced, perfectly stable, and it's not alone. Roman harbors built directly into the sea still exist, their concrete foundations hardened by constant exposure to salt water. Modern marine concrete degrades in decades. Roman marine concrete thrives. It literally reacts with seawater to form new crystalline structures that make it stronger over time. That shouldn't be possible. Salt water is supposed to destroy concrete. Chloride ions penetrate, steel corrodes, cracks expand. That's basic material science. And yet, Roman concrete breaks that rule. So the question isn't, was Roman concrete good? The real question is, how did they do this? And perhaps more disturbingly, why did we forget how? To answer that, we need to go back, not to emperors or legions, but to a gray, powdery substance pulled from the earth near a volcano. Because Rome's greatest construction secret didn't come from marble quarries or limestone pits. It came from ash, volcanic ash. Specifically, ash from the region around Mount Vesuvius and the Bay of Naples, known to the Romans as pozzolana. At first glance, pozzolana looks unremarkable, fine, dusty, reddish-gray soil. But mixed with lime and seawater, it triggers a chemical reaction unlike anything in modern Portland cement. Instead of forming weak, brittle compounds, Roman concrete produces rare minerals, aluminum tobermorite and philipsite, crystals that grow over time, knitting the concrete together at the microscopic level. This isn't accidental. This is chemistry. The Romans didn't know the words crystal lattice or mineral hydration, but they knew results. They tested mixtures, they observed failures, they refined proportions. Vitruvius, Rome's great architectural theorist, wrote about concrete formulas with the same seriousness modern engineers reserve for structural equations. He understood that certain volcanic materials behaved differently in water. He understood durability, and the Romans exploited that knowledge on a scale. They poured concrete underwater. They cast entire harbors in the sea. They built breakwaters that absorbed wave energy instead of resisting it. Modern concrete fights nature. Roman concrete partnered with it. And this philosophical difference may be the key to why their structures endure while ours decay. But Roman concrete wasn't just about chemistry, it was about strategy. The genius wasn't merely that the material was strong, it was that it allowed forms and structures no civilization had ever attempted. Arches, vaults, domes. Concrete freed Rome from the limitations of stone blocks and straight lines. With concrete, Romans could pour curves, span vast spaces, and distribute weight in ways that made their architecture feel almost impossible. This is why Roman cities didn't just grow, they expanded vertically and horizontally with terrifying efficiency. Aqueducts crossed valleys, bath complexes covered acres, amphitheaters rose like artificial mountains, and all of it depended on a material that behaved in ways modern concrete simply doesn't. But here's where the story takes a darker turn, because despite all this brilliance, Roman concrete vanished. Not immediately, not dramatically, it faded. As the empire fractured, supply chains collapsed, pozzolana sources were abandoned, knowledge passed through apprentices instead of institutions. By the Middle Ages, builders still used lime mortar, but the precise recipes, the volcanic ash chemistry, the understanding of underwater curing, gone. Stone replaced concrete, thick walls replaced elegant domes. Engineering regressed, not because people were less intelligent, but because the system that preserved the knowledge no longer existed. And when modern concrete emerged in the 19th century, it followed a different path. Portland cement prioritized speed, standardization, and scalability. It worked, but it sacrificed longevity. Steel reinforcement allowed taller buildings, but introduced corrosion. Efficiency replaced permanence. And only recently, within the last few decades, have scientists begun to ask an uncomfortable question. What if the Romans were right? What if our ancestors already solved the durability problem, and we just stopped listening? When researchers began analyzing Roman concrete under electron microscopes, they found something shocking. The material wasn't uniform. It was heterogeneous, full of lime clasts, mineral inclusions, and microstructures that modern engineers would normally consider flaws.